Oh, welcome. 5-5. Lot of information 5-5 here. We're going to learn how to solve equations of polynomials that aren't quite so obvious. Where, if you got something where you can factor it in one of the many ways we factor it, then it's not so bad. A factor might be grouping. You might have to break down an x to the fourth into an x squared and an x squared. But here we're going to have some problems that you're like, man, I can't factor these. Yeah, obviously I can't factor them. But there might be some factors that you can come up with by using what we've been doing here with the synthetic division. So today we're going to use what's called the rational root theorem. We'll lead off with that. And then we'll also use the conjugate root theorem. I don't know if you guys remember what conjugates are, but if I've got a plus b, the conjugate's a minus b. So 2 plus square root 3 would have a conjugate of 2 minus square root 3. Okay, so first off, rational root theorem basically states that if we're looking for roots of a polynomial, like if I say 2 is a root, or a 0, 0 and root are synonymous. That would mean that if 2 is a root, it would mean that x minus 2 is a factor. Okay, or rational makes me think ratio or fraction. That's a little bit trickier. So 2 could be 2 over 1, but maybe we got a rational root of 3 halves. Well, having a rational root of 3 halves actually tells me that 2x minus 3 would end up being a factor. Because if I set 2x minus 3 equal to 0, I'd add 3 and divide by 2. So I'd have a rational root of 3 halves. Okay, so we're going to try to find all the fraction roots, and that will allow us to factor our polynomials. So what the rational root theorem states is that if you take the constant term, which in this case is 10, and write all the factors of 10. So what goes into 10? Well, 1 goes in there 10 times, and 2 goes in there 5 times. And then you take all the factors of your lead coefficient, which in this case is 5, and when that goes into 1, the 5 is 1 and 5. If you take those factors and write them as fractions, you've got all the possible rational roots. Now what needs to happen is you need to put the constant factors over the lead coefficient factors. That's essentially what's being set up here. But also keep in mind that it doesn't have to be positive. You can also have negative. So what I'm going to do is say, okay, my possibilities are plus or minus, and then I'm just going to go through each of the factors of the constant. In this case 1, and then put it over each of the factors of the lead coefficients would be 1 and 5. So I'd start off with 1 over 1. Well, that's 1. Then I'd have 1 over 5. That's a fifth. Then I go down the line and I say, okay, what about the 2? Well, I'd have 2 over 1, which is 2. And then 2 over 5, which is 2 fifths. We go to the 5. 5 over 1 is 5. 5 over 5 is 1. Well, I don't need to write it again. I already have 1 as a possibility, so I'm not going to write that again. And then finally, I've got 10 over 1 is 10. And 10 over 5, well, that's 2, but I've already got the 2. So there are 1, 2, 3, 4, 5, 6 times 2, because plus or minus there are 12 possible rational roots that could go into that polynomial. This problem I didn't have you show which ones or if any of these actually work. We'll do that on the next problem. So once problem on your test, you're just going to have to simply list all the rational roots just like this, and the answer would be plus or minus 1, 1/5, 2, 2/5, 5, 10. Okay, example 2, we're going to list all the factors of the constant, which are 1 and 6, 2 and 3, and all the factors of the lead coefficient, which, be careful, I'm trying to trick you here actually, it's not 10, it's -3, because that would be the lead term, because it's x to the fourth. You don't need to worry about the negative, because we're going to do plus or minus anyways, so you can just say, I'm going to look at 3, and we'll use 1 times 3. So possibilities, plus plus or minus. 1 over 1 is 1. 1 over 3 is a third. 2 over 1 is 2. 2 over 3 is 2/3. 3 over 1 is 3. 3 over 3 is 1. We already listed that one. 6 over 1 is 6. And 6 over 3 is 2, and we already listed that. So this one also has 12 possible factors. Alright, example 3. List all possible rational roots. And then determine if any truly are roots. Okay, so this one's a little bit more involved. So we're going to do the same thing. We've got a constant -6, but I don't care that it's negative. We'll just put 6, and then the lead is 2. So 6 is 1, 2, 3, 6. 2 is 1 and 2. Possibilities, plus or minus. 1 over 1. 1 over 2. 2 over 1. 2 over 2 is 1. I already did that. 3 over 1. 3 over 2. 6 over 1. And 6 over 2 is 3. So there's my possibilities right there. Maybe you could also do 1, do 1 over 1, 2 over 1, 3 over 1, 6 over 1, and have the 1, 2, 3, 6 first, and then do 1/2, and then divide each of those by 2 after that. I don't care how you list them, just so you get all 6. And of course it's 12 because plus or minus. So get all 6 on the inside, get your plus or minus on the outside, you've got your 12. Okay, so how do I determine if any of them truly are roots? Well, if any of them are roots, that tells me that when I divide 2x cubed plus 3x squared minus 11x minus 6 by one of these, I should have a remainder of 0. So that's what we're going to have to prove. We're going to take the 2, 3, the -11, the -6. And back in my day, I had to go, okay, so a possibility is 1. So I tried 1, and then I did my synthetic. Drop the 2, 2, 5, 5, -6, -6. Oh, so close. I wish it would have been +6 because then it would have canceled. I got -12. 1 didn't work. So, all right, 1 didn't work. We got to do this up to 12 times. So we're going to try, I try -1 next. That's easy to try. 2, -2, 1, -1, -12, 12. That didn't work. I need to get 0 at the end. So it's not 1, it's not -1. I'm not real keen on using the fractions, so I would actually probably do the integers first. I'd try 2 next. 2, 4, 7, 14, 3, 6. There we go. Hey, look, I just found it only took me 3 times. So that wasn't too bad. I found out that 2 is a root. Well, once you get down to, we don't need to keep trying these. Once we get down to 3 terms down here, 1, 2, 3, you need to realize that that's quadratic. And once you have a quadratic, go ahead and just try to factor it. So I just proved that 2 is a root, because there's a 0 at the end. But I'm going to see if I can actually factor 2x squared plus 7x plus 3 to see if there are any other roots. It has to be 2x and x, because 2x times x is 2x squared. It's got to be plus and plus. And 1 times 3 or 3 times 1. Well, it looks like it's got to be 1 and 3, because that would give me 6x plus 1x, which is 7x. So once you get to a quadratic, go ahead and factor it. And that's a perfectly good way to show that you've got a root. And I see that the roots are -1/2, -1 divided by 2, and -3. So what are roots? 2, -1/2, -3 are roots, or zeros. It means the same thing. To simplify this, so we're not sitting here guessing. I mean, well, it would have been a shame to go through 11 of the 12 and then finally get to the 12 and go, oh, this one works. Rather than do that, you could go ahead and plug this in your calculator and narrow down your choices. So what do I mean by that? Let me bring up the calculator. Let's go y equals. I don't think I need this anymore. I'll clear this out. Clear this out. And then let's type in what the problem was. 2x cubed plus 3x squared minus 11x minus 6. we got 2x to the third plus 3x squared minus 11x minus 6 minus 11x minus 6. I'm going to zoom 6 this so I get my standard window. And then what am I looking for roots, guys? I'm looking for roots are the zeros. So I'm looking here, here, here. There's 3 of them. And that helps me narrow down what to try. This looks like it crosses at -3. This looks like it crosses at 2. This looks like it's between 0 and -1. So what are some possibilities between 0 and -1 that I had up there? I think the only possibility was -1/2. Again, you could go to your table and show that -3 and 2 both work. Go second graph. And you see at 2 I get 0. 2 I get a 0. That's a root. And then at -3 I should also get a 0. If that's right, and I do. See, -3 I also get a 0. You'd have to change your table set in order to show that the -1/2 is 0. But doing it synthetically or by factoring is what we're looking for anyways. So it's not like you need, once you have one that works, once you say, hey, I see by the graph 2 works, put this 2 right here, do the synthetic, and then you can do the rest by factoring. Okay? All right, so that was rational root theorem. Moving on, we've got the conjugate root theorem. And that basically says that irrational roots have to come in pairs and imaginary roots have to come in pairs. So if you've got a plus square root b, that means that you also have to have a minus square root b. Or if you have a plus bi, you also have to have a minus bi. So we built polynomial functions a couple lessons ago. We're just doing that same thing. It's just recognizing that, hey, if I have an imaginary, I have 2 imaginaries. Or if I have a root, I have 2 roots. So example 4, build a polynomial function with rational coefficients that has roots of 3i and 5i. Well, I know that that actually has 3 roots, because for it to have 3i, it also has to have -3i. So there are 3 things to write down and build our function. First, there's a 5. That'd be x minus 5. That's the factor. That would give me a 5 over a root, or a 0. Then there's an x minus 3i. There's also then an x minus -3i, which is x plus 3i. And you need to multiply those out. Well, this really isn't too bad. It looks a little ugly, but what we have here is when you multiply conjugates, just remember the middles cancel out. So all you need to do is take the first times the first, and the last times the last. The middles would cancel out. The middles would be 3ix and -3ix. They cancel out. Well, what do I get at the end? I get minus 9i squared, which remember is plus 9. So if you've got conjugates, multiply those out first. Now, if you had taken x minus 5 times x minus 3i, that would have been a mess. And now it's just boiling out. X times x squared is x cubed. X times 9 is 9x. -5 times x squared is -5x squared. And -5 times 9 is -45. So you've got x cubed minus 5x squared plus 9x minus 45. Go f of x equals that. I suppose I should put that to make sure that we have a function. F of x equals that, because I said polynomial function. Okay? Alright, this one I think is a little trickier, because we've got a coefficient, or a root of 2 minus 5i. So that tells me that I've got to do 2 plus, or not 5i, 2 minus square root 5, and 2 plus square root 5. So that tells me, you might need to rewind this one, take your time, that x minus 2 minus root 5 has to be a factor, and x minus 2 plus root 5 has to be a factor. So I just subtracted each of those. Well, I'm going to go ahead and distribute the negative and change these. So it'd be x minus 2 plus root 5. I distribute this negative. And x minus 2 minus root 5. Which you could take x times all 3, then negative 2 times all 3, and then square root 5 times all 3 and add like terms. But there's a simpler way. Here it is. You could group the x minus 2 and the x minus 2. If I group the x minus 2, I have conjugates. I have the situation where I have a plus b times a minus b. In this case, what's a? Well, it's x minus 2. And what's b? It's square root 5. And when I do a plus b times a minus b, all that is a squared minus b squared. So I like to do this like this. I take x minus 2 times x minus 2. That's x minus 2 squared. So I take the first one squared, then I subtract the last one squared, which is square root 5 squared. Now we simplify. What's x minus 2 squared? Squared answers. It's first one squared, twice the product, last one squared. Minus, what's the square root of 5 squared? That's just 5. Add like terms. Go to the left of x in front of here. You got x squared minus 4x minus 1. Yeah, you could have multiplied, you could have FOILed each of the 3 terms by each of the 3 terms, but it ends up messier. This is a lot slicker way, so I encourage you to welcome it to your world. Build a quartic function that has roots of 3 and 5 plus 2i. Quartic, well, since I have 5 plus 2i, that means I have 5 minus 2i. But for quartic means I have 4 roots. And I think I should have said that has only roots. Because I don't want you just making one up and say, oh, let's just pretend it has a root of 1. I want only roots of 3 and 5 plus 2i. So I have 5 minus 2i has to be 1, but that would give me a cubic. I need another root. Well, to get another root, that must mean that there's a second one of these. That must mean that 3 has a multiplicity of 2. So instead of just putting x minus 3, you have to say, oh, I have to have 2 of those. And then I have x minus 5 plus 2i. Make sure you minus the whole thing. X minus 5 minus 2i. Ooh, scary. We can do this. Let's clean the stuff up on the right here. Let's change this to x minus 5 minus 2i. X minus 5 plus 2i. Okay, so this is going to practice what we just did on the previous problem. Let's group the x minus 5s and realize that I have conjugates. I've got a minus b, a plus b. So I need a squared, x minus 5 squared, minus b squared, 2i squared. A squared minus b squared. Well, what does that turn into? Square dance this. I get x squared minus 10x plus 25. First one squared, twice the product, last one squared. And then I get minus 4i squared, which is plus 4. So my right-hand side would have turned into x squared minus 10x plus 29. My left-hand side would be first one squared, twice the product, last one squared, x squared, so I'm just squaring that. And then now I'm going to multiply these out. This one's a little painful. Some people are using a box method. That's actually kind of, I think, kind of neat when you're doing the 3 by 3. You want to see that, it has to be separately. Otherwise, here we go. X squared times x squared. X to the 4th minus minus 10x cubed plus 29x squared. Negative 6x times x squared is negative 6x cubed plus 60x squared. Oh, let's see, we got 6 times 29. That's a 29 up there. 6 times 30 is 180. So 36 is 180. 29 sixes would be 1 less 6 than 180. So that'd be 180 minus 6, 174. So negative 174. Oops, let's tidy that up. Negative 174x. And then last one here. X, let's see, 9 times x squared, 9x squared. Negative 90x. And then 9 times 29, well 9 times 30 is 270. And I gotta subtract 9 from that, so 261. Alright, so what do I get? Add those down. And if I add those down, I get f of x equals x to the 4th minus 16x cubed, 38 plus 98 x squared minus 264x plus 261. That is about as tough as it gets. Okay, it's been a very long lesson, I know, but hey, it looks like we got one problem left, so let's fight through, get it done. Find the zeros of f of x equals, given that 3i is 0. That tells me if I plug in 3i synthetically, that I should get 0 at the end. Wow, does that work? Well, first off, when I do 3i, I'd better leave some more room between numbers. So let's go negative 1, 14, negative 9, 45. This is kind of cool. So I'll bring down the 1. 1 times 3i is 3i. Add, you get negative 1 plus 3i. What's 3i times negative 1 plus 3i? Well, it's got a negative 3i. And then what's 3i times 3i is 9i squared, which is negative 9. Add straight down, I get 5 minus 3i. Take 3i times both of those. 3i times 5 is 15i. 3i times negative 3i is negative 9i squared, which is positive 9. Add straight down, you get 15i. 3i times 15i, 45i squared, negative 45. Tells me I get a 0 at the end. Just show that 3i worked. Well, if 3i works, that means negative 3i has to work. Guess what? We're going to do this again. We're going to use these same numbers that I have right here. I'm not going to rewrite it. I'm going to put a negative 3i right here. And negative 3i should work with what I have left. And this would be pretty ugly if I tried to write it out. It'd be x cubed plus the quantity negative 1 plus 3i times that quantity times x squared plus the quantity 5 minus 3i, that quantity times x, plus 15i. That's not good to look at. But now watch, if I use negative 3i, drop the 1, multiply, get negative 3i. Add, get negative 1. What's negative 3i times negative 1? It's 3i. Add, get 5. What's negative 3i times 5? Negative 15i. Add, you get 0. Look, we just show that we have 3i, we have negative 3i. What am I left with? I'm left with a quadratic. I've got 3 terms. Once we get to 3 terms, think quadratic. Quit with synthetic. Think quadratic. This would be x squared minus x plus 5. If you could factor that to find the other zeros, do so. We can't factor it. So what are we going to do? You got 2 choices. You could either complete the square, which I wouldn't advise, or do the quadratic. X equals negative b plus or minus the square root. B squared minus 4 times a times c all over 2a. 1 plus or minus. The discriminant would be 1 minus 20, negative 19, all over 2. Simplify. 1 plus or minus I root 19 all over 2. So, if I write that in complex standard form, my zeros would be 3i, negative 3i, -1 plus or minus square root 19/2 I. Or I could put plus or minus right here too, I guess. There's my 4 zeros. That is quite complicated. If you get that, you're sitting pretty. We will do more of what we just did here on this problem in the days to come, where we plug in a 0, we get a 0 here, and then we use what's left to break it down some more until we get to a quadratic.